I'm delighted and honored to be hosting today's session and to welcome both our speakers to talk, which is titled Collaborating to Build AI-Ready Biolabs. So this session brings together two of the best thought leaders from academia and industry to explore how engineers, researchers, and partners are working together to integrate AI into their biomedical lab environments. We'll be looking at practical research projects that move beyond hype and kind of towards real time and performance that deliver both clinical and economic impact. So before I even hand over the mic, I kind of just want to take a moment to kind of introduce both our speakers and to give you a bit of their background. So our first speaker is Dr. Shane Loughlin. So he is the president of the Equipment Systems Engineering, ESE for short, of the ESE Academy, and he is a prominent figure in digital transformation for the life sciences sector. With a strong engineering foundation and decades of experience working with leading pharmaceutical and medtech companies, Shane has helped spearhead and shape Ireland's approach to Industry 4.0. He is the driving force behind the creation of Ireland's first level 9 Masters in Equipment Systems Engineering, which he has developed in collaboration with the University of Limerick. What it does is it bridges the gap between academic research and real-world implementation. Shane's work blends both academic rigor with practical innovation, contributing to both the development of national digital capability frameworks as well as the mentoring of engineering professionals in regulated, high-impact environments. Our second speaker is Professor Daly. So Professor Daly, he is an associate professor in biomedical engineering at the University of Galway and a funded investigator at Curran as part of Science Foundation Ireland's Research Centre for Medical Devices. He currently leads the Biofabrication Research Group, which focuses on developing innovative bioprinting technologies to engineer tissue and organs with enhanced structural and functional properties. His interdisciplinary team includes experts in biomedical engineering, biomaterials, computer science, biotechnology, and stem cell biology. Professor Daly's research has been published in leading journals such as Nature Communication, Nature Review Materials, Cell, and many more. To date, he has secured over 2.4 million euro in research funding, and some of his projects include the ERC-funded MorphoPrint, which aims to develop new biowinks for organ bioprinting, and other projects such as the Science Foundation Ireland-funded AI-Print, which focuses on AI-powered 3D bioprinting technology. His work aims to advance physiological relevance of engineering tissues, facilitating their application in drug screening platforms, and as well as transplantable grafts for tissue repair. So that's just a bit of taste. Now, to be honest, this is only a taste of what they've done so far. So I would encourage you to reach out to them after this seminar and just kind of see what else they've achieved, because we'd be here all day if I was to list everything. So I'm just going to hand over the mic to Andrew, if you want to go ahead there.
So thank you, Johnny, and also Shane for, I guess, the invitation. So it's great to be speaking today. And yeah, as Johnny introduced, my group is focusing on bioprinting, specifically heart tissue is our ultimate goal. So I'll give you a flavor of two projects that we're currently working on in the lab. So heart tissue engineering, the overall goal is to be able to create implantable grafts that could be used to repair or replace damaged heart tissue. Obviously, this is a very challenging problem, so we need to be able to take cells, stem cell derived heart cells, add them onto materials that will allow us to grow functional tissue that could be implanted to regenerate potentially diseased tissue. So from an engineering perspective, this is really interesting and challenging. So this is what a human heart cell looks like when it's been cultured on a cell culture dish on its own. So you can see it's contractile. You can see the machinery driving the beating of the cell. And what we are quite good at is actually scaling these processes up. So how do we scale this and print it or turn it into a tissue that could actually have some therapeutic contractile effect once it's been implanted into the body? So this is just a recent video we've taken from a printed piece of heart tissue. I'll go through how we developed this and being cultured for up to 3 months, and you can see it is actively contracting. So in here we have about 250 to 300 million cardiomyocytes kind of synchronously contracting together. So maybe to kind of start at the most basic level, so where do we actually get human heart cells? Obviously, we can't isolate them from a human. So we take a route where we develop them from induced pluripotent stem cells. And this is our protocol for generating them. So we can start off with pluripotent stem cells, basically meaning that they can turn into any cell type in the body. We give them the right cocktail of factors inhibiting certain biological pathways that eventually turns them into cardiomyocytes. And what you're looking at here, I know some of you may not be familiar with these type of staining techniques or imaging techniques, is markers just basically proving that they've gone from a stem cell into a cardiac cell. And if we look down the microscope after a week or 10 days of this protocol, you can see the sheet of beating tissue. So here you're probably looking at about 80,000 cells just in this little cross-sectional area. So this is obviously very promising, although we couldn't just take this and implant it right now. It's quite a thin sheet of tissue. It would not generate sufficient contractile force to have any kind of therapeutic effect on the heart. So we basically take these cells, we introduce them into our bioprinting system. I'll go through this gradually. But this is an extruder where we can combine cells kind of denoted in this schematic in red with a bioink, which is green. We use collagen for a lot of our work because it's the natural ECM component in a tissue. And we can print three-dimensional structures. And so this is just a video looking at underneath the printer. So we have a camera here, and you can see a gel getting extruded out of the nozzle. So inside that gel, it's a mixture of collagen and also hyaluronic acid. So two natural ECM components. We have our cells, and you can see here building up this three-dimensional structure. I won't go into it in today's talk just because of the time limitation, but we've done a lot of work on optimizing the rheological properties to be able to print these fluids quite accurately and kind of optimize the flow rates and use this process to build up 3D structures. So, and then just to kind of think about the length scales here. So inside this ink that we're extruding, we have collagen fibers, and we have hyaluronic acid that gives the material a high viscosity, so we can extrude it accurately. And embedded within that, we have cells. And optimizing these materials so they have the right properties that you can print them, but they can also support the development and maturation of cells into a tissue post-printing is really where the challenge is at in bioprinting right now. So this is just an example of the same printing process. So you can scale this up, obviously, to build three-dimensional structures. So this is taking an STL scan of a human heart. And we can have cells inside these structures. But the real challenge is if we actually compare the organization of printed cells to real adult myocardium or real muscle, and we can see there's pretty big differences. So the muscle in the heart is obviously very aligned. It's got this kind of twisting structure to optimize the contractile output. And if the printed cells do not have this kind of same organization, they're going to lack the functionality needed for transplantation. So we're trying to develop methods to go from something like this into something more realistic that would have similar kind of properties to control the electrical signaling and then maximize the contractile output. So big challenges are replicating the very high cell density. So cardiac cells are very, very tightly packed together, and they're also structurally aligned, giving them their function. So the first project we're working on, and I'm going to talk you through quickly, is where we're taking inspiration from organ development and how the heart actually forms in the embryo. And it's quite interesting from an engineering perspective. It actually starts off as a simple tube that over time undergoes different types of twisting and bending, eventually forming kind of an early four-chamber structure. And these are some images from a developing heart in the embryo. So these changes and these mechanical forces that happen during this process are crucial for sculpting the structure. So that's what gives cardiac tissue its actual alignment. So over time, these shape morphing patterns sculpt the cell and tissue maturation. And so we're currently developing techniques where we can incorporate this. So we might print a tube of tissue that has heart cells, and then we can guide it through a shape morphing process to improve its structural and functional maturity. And we think because if we can do this, if the tissue is forming how it naturally does during development, we would get a much more mature tissue at the end of the process. So breaking down cells and tissue evolution during morphogenesis and tissue development. So if we think of a cluster of cells, over time, it's going to turn into something with a different shape or more functionality. And this is due to spatiotemporal variations, maybe in tissue mechanics or growth that govern this. So and to break it down from an engineering perspective, we have material addition, we have forces acting on this tissue, and we have also material properties. And those three things combined will give you a morphogenetic flow, which will change the structure of the tissue. So from a biological perspective, material addition is just cell proliferation, so more cells, and forces are generated by cells. So cells actually can pull on extracellular matrix and generate their own force. Um, so the first project I'll quickly go through is taking this idea of cell-generated forces to bioprinted tissue that changes shape over time. And so this is work from Ankita Pramanik, a fourth-year PhD student who actually was awarded the Engineers Ireland Biomedical Research Medal in at Loughlin back in January for the work I'm about to go through. But what basically Ankita developed is she first started looking at what happens printed tissues over time. So if we create a geometry such as a tube, you see over 14 days of culture in the incubator, it will kind of shrink into a smaller tubular structure that you can see here. But if you change that initial geometry, you get quite a different behavior. So you can see, for example, this spiral kind of opens and uncurls, whereas this M-shaped structure kind of opens at the ends here. And this is driven by the forces that the cells are actually exerting on the ECM and on the collagen fibers. So we can scale this up, and these are just the input CAD files looking at a kind of a bent tube or a tubular M-shaped structure here. And this is kind of looking at a larger scale from the side. You can see this tissue over time, over 7 days of culture, changing shape and morphing. And this is kind of the culture bath that we maintain them in. We're also able to computationally predict what will happen to tissue too. So this is a collaboration with another lab here at the University of Galway, the McAvoy Laboratory. And they're experts in developing models that can predict how cells interact with extracellular matrix, generate stress, and what will happen to those structures over time. So we can create a digital twin, essentially, of the shape morphing process that you can see here. And we actually do get similar outputs when we bioprint a tissue. So this is experimental data here on the left, and this is computational data on the right. And we've compared them. So this is quite powerful because we can use it as kind of an inverse design tool to see what might happen our printed tissue experimentally. So just to kind of link this back then, so in terms of the alignment and the structure that I talked about being very important, we're now looking at how this changes over time as these tissues kind of morph and twist and change shape. And interestingly, we've seen if we use confocal microscopy to look at the organization in high resolution, you can really see that it's kind of aligned along the principal tissue axis. So in the case of this tube that you can see here. This is just kind of quantification. If we just focus on this bottom one, we're looking at a protein here called fibronectin. And if we quantify the alignment of that at day 0 and day 14, you can kind of see from this polar plot that it's kind of emerging over time. And nicely as well, we're able to computationally predict this too. So with cell and collagen alignment kind of following the principal strain within the tissue. So just to kind of finish then on this, if these are actual videos of printed tubes contracting in the culture dish, so this is a viable tissue. You can see synchronous contraction across the tissue. We have looked at the actual sarcomeres, which are the force generating kind of subunit within the cardiomyocytes, and we can see that they're starting to develop more mature phenotypes that better matches adult cardiac tissue. And we're able to scale this up into larger scale structures, such as a double ventricle that you can see here. And so this red staining just tells us where there's cardiomyocytes. And vimentin is another cell type called a fibroblast that's in the tissue. So these are kind of in the right proportion. And this is just a kind of a scaled up tissue beating after, this is at 2 weeks of culture right now, but we're currently looking at at much longer term cultures. So what we found here is that by kind of creating these shape morphing tissues that go through a developmental like process, we can really improve their maturation and their, their physiological relevance post printing. So I'm just going to skip through this last slide on that in the interest of time. So the second project I'm going to talk to you about is more recent work on AI-powered printing. And the reason we're getting interested in this area is while bioprinting hardware has been advancing over the last number of years, there are a lot of critical limitations. So just as an example, this is if we give an input CAD model to one of our bioprinters, and even with lots of optimization, kind of material optimization, parameter optimization, it's often difficult to get outputs to precisely match the input CAD file. So we can see that there's areas of over extrusion happened in this case. So there's limitations with precision and reproducibility. And while that's okay for kind of research grade experiments where we're looking at function, translating this into clinical products, this limitation does really need to be fixed. So this is a Research Ireland challenge funded project. And our goal here is to develop a printer that can actually watch itself and correct itself when something goes wrong. So we're using microscopy to actually monitor the print process in real time. We're collaborating with the computer science department to develop convolutional neural networks that can classify, say, when the printer is over extruding or under extruding. And we could take that state then to implement an action that might cause the printer to correct it on the fly and in real time. And we're exploring how we can improve print accuracy, reproducibility, precision with that. So this is just one of our current prototypes. So it's just a extruder that, turn off the sound there. So this is a pure dyeing extruder where we put our bioink. We're using a relatively simple frame system right now. It's okay for current purposes. And we've got a camera tracking the nozzle underneath. And you can see we get this nice live view of the printing process. And this is work done by Daniel Kelly and Vasilius Sergius. So Vasilius developed a really nice computer vision platform where he can actually in real time compare the extrusion outputs to the input CAD files and get real-time accuracy measurements. So looking at how much overlap we have between our CAD file and what we're actually printing. So that's quite useful when we're trying to optimize or make our protocols more reproducible. So we're also developing CNN models. So we can generate lots of data using these systems. So for example, these are images of good extrusion, under extrusion, or over extrusion. These were deliberately input. We've done this for cases of single line and infill extrusion as we build up our structures. We can create lots of data, so hundreds of thousands of images which are needed to train image recognition algorithms such as CNNs. And we're then taking those CNNs and actually deploying them on the printer. So I'll skip through this here, but basically we're able to get quite high accuracy. So with the CNN models that we've actually trained for print error detection, we can get about 90 to sometimes 95% accuracy, depending on the type of neural network we're using. And these are some of the different neural networks that we've actually tried out. So what this has kind of resulted in is a system where we have a printer monitoring the output. We're feeding those images or live videos to a convolutional neural network. That's classifying the state for us. And then we're using that data to implement extrusion adjustments in real time. And this is kind of the display that we have right now. So you can see here printing just the first layer of the structure. We've got a current classification based on how the model has been trained. We got cumulative error building up over time. So 85% of this has been good, and 17%, for example, has been over extruded. And in terms of accuracy of the model, in terms of files that we know have certain errors, we can get quite high prediction. So just maybe the final thing that I'll show you here is this is our model running on two different scenarios. The top scenario we have no AI running on the model. So this will be an over extrusion got introduced at this point and an under extrusion at this point. And on the bottom panel is when we're actually running the model in real time. And what you can see is if I just kind of stop it here, I think you can see in this case, the over extrusion has kind of built up and we have a defect. And down here, when we were running our model, it was corrected within about 6 to 8 seconds currently is what we can do, but we're trying to improve this. And here you can see we improved the output with our AI model compared to the control over here. So yeah, and I'll skip through that. That's basically just quantification of it. So yeah, and we've recently put this out. If anyone is interested in looking at it, including the models that we actually developed. So yeah, so I'm a little bit over time, but thanks. Hopefully that was made sense. Just to thank everyone in the lab, and particularly Daniel and Vasilius, who did the AI printing work right now, and also Ankita's work, which I showed at the start, and also just to thank the funding sources as well. So yeah, thank you very much.
Hi everyone, I'm Shane Loughlin, president of the AC Academy. I'll just give a very brief introduction because I've been around quite a while. I've started off as an instrument technician and I've gone through all the different layers of the qualification network within Engineers Ireland and so on. So that gives a pretty unique perspective. But in 2002, I set up SL Controls, so we're an equipment systems integration company, focused first of all in semiconductor and then high-speed manufacturing, and then specializing in life science. Last year, I stepped down from SL Controls, and we had fully integrated into NIT, a global IT corporation, so that we can span the IT and OT layer. But as part of the PhD, the majority of my work was focusing on developing frameworks. A lot of clients asked me to explain how do you go about the process of procuring equipment so efficiently for the life sciences sector. And as part of that, I did the doctorate level research in TUD and published it in Creative Commons to share it generally with the industry. And that resulted in us being asked to set up the ESE Academy. So the ESE Academy is an academy solely for the occupation of equipment systems engineering. It's not a profit-based structure. It's a sustainable business model structure, CPD structure. And that's helped us focus with University of Limerick at the time for creating an M-Eng in mechatronics, full-time one, and an M-Eng in equipment systems engineering. And now what we're focusing on is creating best practice guides for biolabs. And we're doing this under a structure, it's only a structure, as ESE Biolabs. And we'll hopefully give the overview there on how we want to share the insights that we have. One of the key partners in what we're doing, because it's all about CPD. It's all as everyone progresses through their careers, there's all these new things that we have to get up to speed on, and we're better to do it than in the structure of a professional organization. And the vast majority of the main players in this space are CPD accredited employers. So it's the ideal location. And under the biomedical division, that gives us a great opportunity to work together and collaborate together. But also, it gives us the opportunity from a professional title perspective, and not just at a chartered level, but also at the other levels. So what's really good is that it doesn't exclude anyone. And I can say that as an instrument tech going the whole way back. So I think that's one of the big items that's very, very encouraging and useful from an Engineers Ireland perspective. So I hope that helps Maureen, but that's my benefit from working with Engineers Ireland. The second part of what we flagged with regard to the presentation that we find is very useful when we explain to a lot of people the perspective we have is the difference between hype and innovation, especially in the life sciences sector. So there's a very useful cycle called the Gartner hype cycle. And what happens when a technology is made available, its visibility increases very rapidly, but with it comes a peak of inflated expectation. And what I would say is be careful with AI, be careful with what's been touted as AI. Some things are being touted as AI and they're not really. And some of them are touted as AI and not fit for purpose for where they have to go. So that can run into what we call a failed project. That's the trough of disillusionment. And we have to be careful to avoid that. And by collaborating and sharing the different experiences, we can help do that and work more efficiently. The second part, Rogers is the guy who explained the diffusion of innovation theory way back in 1983. And everybody's familiar with the bell curve with innovators and laggards and so on. But very few actually take the time to read his definition. So an innovation is an idea, practice, or object that's perceived as new by an individual or any other unit of adoption. And the definition of new is extremely important because newness need not involve new knowledge. And quite often, the most radical leaps in performance comes from when you take something that is very high TRL, technology readiness level, in a different domain and bring it into your domain. So the newness may be expressed in terms of knowledge, persuasion, or decision to adopt. So a lot of the AI solutions that we've had for years in the control space, there never was a decision to adopt. So thank you very much, ChatGPT and all the rest. It's all getting a lot of focus now. But it's important that we use the proper AI for the proper solution in the proper phase. And we have to be cognizant of the sector we work in. So in the life sciences sector, this is very, very useful from the Cancer Progress Report. 3 to 6 years can be spent on discovery, followed by 6 to 7 years in clinical trials. And this is typically the space we live in, the scale up to manufacturing. We're given maybe a year to actually scale it out. Scale it up, I should say. So by scaling up, then what can be produced in very small volumes in the lab, we can scale it up to very large batch production. And that method of operation is also endorsed with regard to the innovation chain by the EU. So there's the perception that discovery and research should happen in isolation, followed by innovation in isolation, and commercialization with a little bit of an overlap. But digital technologies now let us share the translational issues that we find and the innovations we find in a co-creation type structure where we collaborate together. So in the traditional world, Andrew and I would never meet. Just wouldn't happen. But Engineers Ireland enable this to happen, which is really fascinating and really powerful. It's also important to factor in the transformational changes that have been happening and that are currently happening or need to happen. So one of the key transformational changes that's been happening in Ireland is the educational transformation. So if we take Mary Liz Trant as the director of the National Apprentice Office, she, with Generation Apprenticeship, together with Anne Ledwith in UL, they collaborated to see how can we use apprenticeships in Ireland. And the apprenticeship structure is very, very powerful for CPD. And that enabled myself and Michael Hennessy to work closely together to see how could we do it. And it's really encouraging that at this point in time, it is now possible for a person to complete their equipment systems engineering level 9 qualification as an apprenticeship. So that opens up the doors to so many industrial practitioners. who really understand those translational gaps and those innovation gaps. So by getting their knowledge and it being shared in a collaborative environment, that's really, really powerful. But it's also, we're not too good in Ireland at shouting out what we do well, but this principal engineer at level 10, that's the first apprenticeship in the world at level 10. And so it's great that that's been endorsed by Engineers Ireland. But that type of experience and ability can then help us to achieve the manufacturing transformation that's required. This is from a very, very good course I'd recommend to anyone. The link is in the bottom from MIT with regard to manufacture of cell gene therapy. For us, we're not in the biomedical space, but just to get the appreciation and the techniques and the words. But what they explained very succinctly is that traditionally you had centralized manufacturing, which then expanded to regional manufacturing. And we do all of that very well in Industry 4. We have Industry 4 and Pharma 4.0, smart factories. And in that model, the equipment is procured, it goes into the factory, and all of the data systems are in the factory that enable you to release the product. But what's totally transformational when we look at the right-hand side is for the brilliant therapies that Andrew and the guys are researching and creating, they have to be manufactured in the hospital. So all of those data systems have to be integrated into the equipment to allow you to real-time release. So Biomedical 5.0 will require co-creation labs. So it will require us to collaborate cross-discipline to co-create these type of solutions. So if we take from the inspiration of Andrew and Ankita's and so on work, which we find really fascinating, we looked at it and we said, okay, how can we share a few insights and some knowledge from the master's apprentices and that we're working with. And the real focus should be on real-time release bioprinting. So not only can I print it, but when I print it, can I stand over it from a legal perspective? And if it doesn't make money, pharma ain't going to release it. So can I stand over it legally and can I make money on it? So to do that, with the perspective of that manufacturing happening in the hospital and all the legalities that go with that, there's a standard called S95 that we use. And if you take in the heading for the Lunch and Learn, the full AI stack, controls in our world are separated into different layers. So at level 0, you have the process, and then at level 1, you have basic control. And that's typically what you buy when you buy the equipment in a scale-up solution. And then we bring it into the plant, and we have supervisory control and manufacturing operation control. We now have to embed all of that into the equipment to meet the manufacturing needs for scaling out. And the architecture we've worked on for to be able to show that and demonstrate it and create the best practice guides for, in that architecture, we can have integrated vision into the control layer and integrated 6D, not just 3D, and we'll show you a couple of videos of where that's at. Integrated 6D control together with the extrusion pump and all of the data systems. And when we look at what that looks like, so I'll just do a check just to make sure to see, are the videos playing okay? Can you see them okay, Johnny? So these are two shuttles that are typically called in this type of a configuration. And we can see here that the trending of the X, Y, and Z can be trended down to the millisecond and even to the microsecond and coordinated and synchronized. What's brilliant with these platforms, we never ever got asked to implement them, is they can do any maths you want, MATLAB, Simulink, etc., but it never gets into the specification. And by us sharing the architectures, we'll hopefully get these requirements into the specification, that when Andrew and then all the other researchers create a model, that model can be directly implemented straight down in the control layer. No human needs to touch it. This is where you're seeing the levitation. So we wouldn't be allowed 3D print with a belt-driven printer overhead because of foreign matter and deposition. But we can print with an Acrobat 6D, and you can see the levitation. And you can see there where we have it moving in the yaw, pitch, and roll, not just X, Y, and Z. Now, we don't know why you'd need that, but it's one hell of a feature to be able to have. And I don't think anybody knows what that will bring. So it lets you re-engineer the process. This is the real-time vision system with integrated AI if it's needed. But there are a lot of features that the existing high-end cameras can do. So when without what we would term AI. So if we take from an overall roadmap, it's been a very exciting journey so far. Because it's only in January that we met Ankita and John Mulville and introduced it to Andrew at the BINI conference. And that gave us the inspiration to actually invest the time and effort in the biolabs term. And this is only from yesterday. And thanks to Dermot and so on, I recognize the voice from yet. But this is actually bioprinting on an Acrobat 6D. So you can see it started to levitate there. Now, we never even used an extruder prior to yesterday, Andrew, so I'm sure there's better ways to do it, and etc. But we will be able to give you and whoever access to this equipment and so on remotely for you to do what you need to do and for us to do what we need to do. And that's the true collaboration. Now, the inspection systems and so on, because we have the links with the technology providers, whatever isn't currently in development, isn't available, we'll get it into their development roadmap if there's a good enough business case and a use case and so on. So there's limitless potential from that perspective. And we'll make it available for the MedTech show if people want and need it. So we'll have 7 or 8 guys working on this all over the summer. And hopefully BINI 2026, people want to see it, I want to see what to do with it. So I suppose that's it in the spirit of collaboration. And just on a closing slide, that ESE Biolab, we'll be using that as part of the equipment systems engineering. I'm not sure. I think maybe it's all full at the moment. I don't know. The girls will know. But and the interesting thing is, because it's an apprenticeship, even somebody with a doctorate can do it. And that's quite fascinating. And fair play to Solus for the investment that they've made in this approach, because it totally changes the CPD. So somebody can be a doctorate level in one domain, but may need to know some of this technology to be able to design the solutions. And that's what we're offering to help. So I'm not sure how we're doing time-wise because I don't have the clock open in front of me, but that's me, Johnny.
Brilliant. You've got great timing. No, that's brilliant. Let me just throw up this slide here. 1 second. We do have a few questions. Just throw up this one here. Just there you go. Just while we're answering some questions. No, thank you both of you, Professor Daly and Dr. Loughlin, just for going through all that. That was very, very, very interesting. Just in terms of, I know Andrew, you might have to pop off in a second, so I might just ask.
Good for 10 minutes. Yeah, sorry.
Yeah, no. So just in terms of your outlook, in terms of what's in your opinion, what do you think is the most exciting short-term application of bioprinting tissue, as well as what's your long-term vision for their role in regenerative medicine?
It's a good question. I mean, there's 2 end use cases. So obviously, if we can make heart tissue that is similar in function and structure to adult heart tissue, that can be used for drug screening applications as an alternative to an animal model, which is, an important part of the pharma development cycle. So There's a lot of work in that area, and we have demonstrated the possibility of using some of our printed models for drug screening and kind of validated that they can give a similar output that has been actually observed in a clinical trial. So I think that's there is potential there, but I think with bioprinting, it's kind of about larger structures that are more anatomically accurate, where it's really more powerful. And obviously, there's a huge clinical need in the case of heart disease. So being able to remuscularize diseased heart, so that's the end goal, obviously. But there's huge translational challenges, and that's why we're starting to work with Shane now, because it's from a hardware perspective, there's limitations to current systems. But also there's lots of work to do in terms of improving the biology. So we actually have a functional tissue. So yeah, I think the collaborating with ESE is going to be very exciting, and I think it gives a lot of opportunity for if as Shane said, if we can start using more robust systems now, that will make translation much easier, rather than thinking about it too late. So yeah.
Yeah, that's great. No, it's definitely great to see the collaboration and just kind of see it emerging and see both of you kind of spearheading the efforts and like putting Ireland at the forefront of all that development. Just in terms of the tissue modeling that you developed in your lab, do you foresee using it particularly in like potentially using for drug screening or like disease modeling efforts, or like what other applications do you kind of foresee using it in your lab when you've fully 3D printed your models?
So yeah, we have used them for looking at microRNA therapies that target cardiomyocyte proliferation. So there's a lot of work on so heart cells are very non-proliferative. As we get older, they proliferate even less. So that's why we have limited regenerative capacity. So we have looked at how our tissues respond to microRNAs that could turn those cells into a more proliferative mode, and compared what we get in our printed model to an actual animal model to try and validate if this model actually gives you useful and predictive insights. So targeting particular pathways. So that's a kind of there's more short term, I think, a short term kind of impact with that application, but in the longer run, we are focused on moving into preclinical models. So looking at if we implant this around the heart, can it actually integrate and help remuscularize the tissue? Can it electrically integrate? I think we need to do a bit more work on that before we start translating there. But as I guess with the second project I showed you, we're also very interested in improving the hardware as well. So kind of making innovations in that road too. Yeah.
Brilliant. And just one last question for you. Sorry, just getting it out of the way because I know you have to hop off soon. Just in terms of like, do you foresee any risks in the advancement of AI if it advances too quickly? Do you foresee any risks in that aspect?
Well, I think in terms of machine control, I think obviously, and we've talked to Shane about this a lot now, is regulation and how it's going to impact that. So we're talking about more physics informed models, or purely mathematical formulas. The advantage here in our particular application is we found that it can really adapt to kind of unseen scenarios quite well and different materials. So when we give the printer a new material that it's never seen before, it can kind of adjust the extrusion properties to that. So one of the biggest challenges in bioprinting overall is that there is actually no clear regulatory framework. There's actually no international standards, which is a big limitation. They need to be developed in terms of, how do you improve the shape accuracy? How do you improve the biological relevance? How are we going to test these things? So that's a huge challenge. And once they're developed, and there also needs to be, is this going to be an ATMP, a combined ATMP? Is it so those kind of pathways and classifications need to be established, and we're starting to get involved in some of those efforts. So I'd say that's kind of the biggest risk. Obviously, if that's not in place, translation and commercialization is going to be impossible.
And we have just a very quick one that came in there. Just in terms of like the main challenges, what have you found like with the 3D printing, like for example, delamination? What have you found were the key variables that you need to control, like e.g., like cell density, pressure, temperature, or like the bioink at extrusion point?
Um, it's it's really about in the case of heart tissue, um, the about 80 to 90% of the volume is cells actually. So and they really need to be connected and electrically integrate. So developing materials that you can actually kind of print, they've got the right viscosity that you can extrude them in a somewhat consistent manner, but that same material can actually support the viability of the cells afterwards and allowing it to mature. So there are two kind of opposing requirements and trying to get materials that best match both of those. So I think we can make a lot of progress. I think soon in terms of improving the hardware, making the geometries more accurate. But the challenge is going to be accelerating. It takes a long time for a heart to actually mature. So how do we actually do that properly in the lab? We also are developing bioreactors, mechanical and electrical stimulation systems, so we can actually, for example, have a tissue getting mechanically stimulated after we culture it and train it essentially. So I haven't really kind of shown that yet because that's at an early stage. So I think the biggest overall challenge will be maturing the tissues in relatively short time spans. Yeah.
And do you think, in terms of the hardware, has it been like developed specifically designed for like bioengineering industry?
Well, a lot of the commercially available hardware is kind of, I mean, the market right now is kind of primarily academics and research institutes. So, there's not, well, at least a current need for types of systems that Shane is working with and has expertise in. But so that kind of that's not yet available. Like GMP grade bioprinters, for example, would be the market is probably not quite there yet because we're still at an early stage. But I think if they're developed overall, I think they would help the field massively. We built most of our printers ourselves. They're very simple to, we just need an extruder. We can adapt it onto a simple rapid prototyping machine by just changing out the material. They allow us to answer a lot of questions that we need to for now, but obviously we need to start working with more robust systems as well.
No, that's all the questions that's been directed to yourself, Dr. Daly. So no, thank you very much thank you. Shane, just in terms of yourself, what are the most significant barriers in the innovation chain when you're trying to implement AI solutions to biomedical labs? And would you have any examples?
I think the first place to start actually, Johnny, is with regard to there are numerous different types of AI. And there's some types of AI that we will never get past regulatory. So we've had the ability to do system identification and model predictive control for 30 years, but nobody wanted it or needed it because the inputs were kept constant and we used statistical process control, and that got us up to Six Sigma. But with these products, the therapies that have to be created, the inputs are incredibly changeable. So statistical process control isn't fit for it. So really, we just need to take system identification and model predictive control out of the toolbox that we have and implement it. The second challenge, so that technology is there. The biggest challenge is that us as people who implement it are typically not from a mathematical background. And we don't typically tend to talk too much to mathematicians traditionally. But we can collaborate now with the mathematicians. So we can put the framework in and they can implement the models as they see fit. So there aren't real barriers. The only barrier, the risk, you see, is when something is implemented and called AI and overhyped, but not practically usable for us. That's when you can have the risk of failure when it comes to translational into commercialization. But we have all the pieces. We just need to collaborate together to make them a reality over the next few months.
Right, right. That, yeah, and that's very interesting because and this kind of points back to like your presentation. You talk about a lot about kind of CPT and growth, just in terms of like if you want to kind of like as an engineer, how can engineers and researchers kind of use CPD as like best practice guidelines to kind of stay current and contribute meaningfully to like AI based transformation?
But that's where Engineers Ireland again is a key partner, because there's two totally different
Mm,
um, scales of from an education perspective. There's even the micro credentials from a university perspective is a 2-year investment by somebody, and that's much too long. But from a CPD perspective, Engineers Ireland has the recognised training provider for recognised CPD. So what we will be doing is summarising a lot of the key language pieces that are needed so that we can talk to each other about what our core application is, our core discipline specific knowledge is. So the objective is for experts to actually summarize the key points so that they can actually have a meaningful conversation with another expert. So, for instance, Andrew's overview there to me is fantastic. It gives me enough information to be able to talk to him, but I do not want a degree in it or a master's in it because I wouldn't be able for it or have the time. So that's where the real core shift needs to come. 1-2 day CPD accredited structures and courses to do the rapid transfer. So to try and answer a lot of the AI that exists in that stack can probably be transferred in a couple of days of CPD training. That's very pointed and very specific. So that's the way we hope to structure it, Johnny.
mm. And in terms of your own opinion, like how would you define like an AI-ready biolab? Would it be more like infrastructure? Would it be like culture or like process? Like what would you see as like the ideal end goal for implementing AI for a
I
ready
think,
bio?
I think for me, where we get caught up and hammered and all the problems, an AI-ready biolab for me is leveraging AI for regulatory.
Mm.
And any AI that isn't of use to regulatory is of no use in such a lab. Um, it's hype is what gets it in the door, but regulatory want maths and science, and we've never managed to give it to them because it was never specified in the equipment. So to me, an AI-ready biolab is a lab that's using fundamental maths and physics for predictive control systems so that you cannot make a bad part. Uh, and that will facilitate real-time release. So that
Mm.
that's where we would see an AI ready biolab, and that everybody who's implementing their AI in the stack has the perspective of this has to be approved and endorsed and applauded by regulatory.
Right, right. And just one last question. Apologies for bombarding you. Just I know you went through a lot of slides there, but just so we have a question here from Charles Smith. So in terms of medical device international regulations are very different to pharmaceutical and biotech regulations. Have you considered that, or what are your thoughts?
Absolutely. But there's huge benefit from implementing the math-centric AI systems and the mathematical digital twin in nearly any process. So if you take one of the first places where we worked with semiconductor,
Mm.
it's not regulated from that perspective, but it's self-regulating based on profits. And they really understand their processes from a mathematical perspective. So the maths and physics-based AI solutions in virtually any sector is really, really strong and really powerful. The second part of where we see the maths and simulation and digital twin and physics simulation is in aerospace and automotive aeronautical. And it's totally from a safety perspective. So the benefits are available to all industry sectors, but maybe in a slightly different variation.
Brilliant.